for today. Let's talk about how we can solve an equation.
Are you recording?
I am recording. Thank you for asking. Okay, let's see. Okay, what about something like that? Say we want to solve it, want to find all complex solutions. That looks like a total mess, right? I mean, but we're to a point where we can handle stuff like this now. We just have to be, we got to get everything on one side. We're going to follow our normal steps, right? We always want to put it in standard form. So where are we going to push everything? Which direction? Left. We want a positive coefficient of the biggest, our leading coefficient we want positive, right? Push everything to the left. So we're going to get 2x to the 7th plus 35x to the 4th plus 216x equals 0. Good. Yeah, that's a little better. Still looks reasonably ugly. Anything else? Oh, you know what? I think I messed something up here. I did.
You know what?
I did. Here, let me go back a little bit. I started to make this trickier, and I forgot I was making it trickier, so I got to do something here. This one. If you watch carefully what I'm doing here, this will kind of give away what the trick is, too.
You already see the number.
Okay, same as before, push everything to one side, right? And that gives us 2x to the 7th plus 70x to the 4th plus 432x equals 0. There we go, that's better. Okay. Now what? Okay, so we could factor out a 2x, right? Okay. So if we undistribute a 2x, what are we left with? Okay.
Pretty dandy right there.
Now we're trying to find solutions to this, right? So we can divide both sides by a constant to simplify things. So what could we divide both sides by, just to kind of make this a little bit easier? We don't really have to. Not by 2x. We can't divide by x, we can divide by 2. Right? We could divide each side by 2, so effectively we're just going to cancel that out, right? It's not a big deal, but we could. And we could have divided the top, one step up, we could have divided everything by 2 if we wanted to also. Okay, so our goal here is to find all the solutions. You can already tell me what one of the solutions of this equation is. Zero, right? By the zero product property, we know that I've got two factors. I've got a really simple one, x, and then I've got a much bigger factor that we're going to have to deal with. But when I set those factors equal to 0, I already know that one solution is going to be x equals 0, right? I need to find the zeros of the other factor, though. So how in the world am I going to deal with that one? Okay, and this takes us back to what we talked about. I guess it would have been like the Thursday before break, right? That's a trinomial. of experience with trinomials. Good, follow your shot. Good job. We've had a lot of experience with trinomials before, right? But they look easier. They look like quadratic trinomials. Is this quadratic though? I mean, it's not. You'd say no, that expression's not quadratic. But I guess what I should say is it a quadratic form?
Yes.
Yes.
Can you make it x cubed?
Oh, okay, good.
Squared?
Good. So that's a quadratic expression in x cubes, right, or in x cubed. If I take it in packets or pieces of x cubed, it does look quadratic. So this whole thing then just looks like x times x cubed squared plus 35 times x cubed to the 1 plus 216, right?
Wow.
We see that? Okay, so it is, if we take it in the right size pieces, it is quadratic. And so we can follow all the same rules we did before. It doesn't matter that that's an x cubed. I just have something squared plus 35 times something plus 216. Well, how did we factor, quadratic trinomials before? What do we always look for? Magic numbers, right? So our goal then here, we just want to find magic numbers again. So this is just x times, if it factors, we're going to have to find magic numbers that multiply to what?
216.
216 and add to
35.
35, okay? So we can do that in a variety of ways. Let's just make a factor list out of 216, right? So we know that if we break 216 up into factors, what are the signs of both the magic numbers going to be here?
Positive.
Yeah, we got to multiply to a positive and add to a positive. So they're both positive. We know that. And we could do something like 216 times 1, but those don't add to 35, right? We're going to have to scoot down the list a ways, because remember, when we're doing these factor lists, the more disparate the values, the higher the sum, right? The more they're different, the bigger the sum is going to be. The closer together the magic numbers get, the smaller the sum is going to be. So let's skip down a ways. What if we did 4? What's that going to multiply by? 54? Okay, that's still too big, isn't it? Right? So let's scoot down. How about 6? 6 won't go into that, will it? 5 won't for sure. 6 won't. Does 6 go into that? I guess it does. 6 and 36, right? Okay, that's getting closer. Not quite. 7 won't work.
Maybe like 8.
How about 8?
7,
8 goes into that. 2 times 2 and 27. There you go. 27 and 8, right? Or our magic numbers. Okay, so we know we've got a plus 27 and a plus 8 there, right? What goes here and here? X cubed. Because those are the things that were being squared, taken to the first power, right? Used to be x's way back in unit 2. Now it's an x cubed. Okay, good. So we broke it down. This is looking much more manageable now. We've got this broken into 3 factors. One of them is done. What about these 2? Can we go further with those? Is that ringing a bell? I know it's been a long break. Probably didn't do a lot of math with the break.
I did.
Yes.
I like
Did
it.
You? How are we gonna go further with those though?
Yeah, you're just gonna. You can figure
No.
it out.
Okay, so let's remember kind of where we left off before break. So if I try to apply the zero product property here, remember, I mean I can.
Yeah, you definitely can.
If I set this equal to 0 and solve, I'm going to get x cubed equals negative 27. Cube root of negative 27 is negative 3. I'll get the value negative 3. Here I get the value negative 2. But I'm not getting all of the solutions then, am I? Right? We know that in this, if we go back to the very beginning, we start off with a 7th degree polynomial, right? So by the fundamental theorem of algebra, how many complex solutions are we guaranteed to have? 7. Now we might have multiplicities, right? We might have multiplicities higher than 1. And so I may end up, some of those might count as multiple roots, right, or multiple zeros. But we got to have 7. Well, we're only getting out, if we just set these equal to 0 and solve, we're only getting out 1, 2, 3, right? And so it looks like maybe we're missing some zeros, and we are. All right, remember the trick now. If we want to take something in this form and find all of the complex zeros of this factor, we've got to use our factoring patterns. Remember the factoring patterns. Okay, let's go back and review those. We need them now, so let's go review them. So you tell me, what was the factoring pattern for something of the form a squared minus b squared?
It's a plus b. Yes.
Good, that's our conjugate pattern, right? How about a squared plus b squared?
A squared plus b squared.
Doesn't factor, right? And for the quadratic ones, you might also remember that when we're doing this whole process, we only have to keep going until we get down to quadratic factors, and then we can bail off the factoring train and just set them equal to 0 and solve. Because once we get a quadratic equation, once we get a quadratic factor in here, when I set that equal to 0, that does take us back to Unit 2. We're experts at that. We know that all quadratic equations in standard form, we can always solve those either by just isolating x and square rooting both sides, or by, factoring if we can, or all else fails quadratic form. But we're always going to get out all of the solutions, both of the solutions there, right? No matter what, we're going to get back both of the solutions easily. But these aren't quadratic yet, so we can't do that. We have to factor this. We can't bail off the factoring tree. We have to continue. Okay, so what about the other ones then? We need the cubic patterns. So what's a cubed? We'll do minus first. What's a difference of cubes pattern? A minus b. Good, because whatever is there goes there, right? Times plus, no, not 2.
AB.
AB. Then the last one's always plus, right? Plus b squared. So whatever goes there, whatever starts off here, if it's a difference pattern, that's a difference. If it's a sum, that's a sum. And then this one's always going to be the opposite. And that one's always plus. So then what's the pattern? We're just going to follow the same rules. What's the pattern for a sum of cubes?
A plus b.
Good. Okay. So what's A and what's B here? Does that look like a sum of cubes?
Yeah.
It does, if I think of 27 as being what cubed? No, 3. Positive 27 is 3 cubed, right? Positive 8 is 2 cubed. Okay? And so now we'll just follow our patterns, right? So this whole thing, let's kind of color code this. So we're going to get,
Let's get back to that last one.
where, back to the last page?
Yeah. Just kind of picture it on that. No. Yeah.
Okay? Okay, so let's make this one green. Okay, what's that going to factor into? We got a sum of cubes, so I'm going to get, I got x cubed plus 3 cubed.
Oh, A plus B.
So x plus 3 times a squared minus ab
3x
plus
9.
b squared, right? Okay, this guy is going to be same deal, but only now b is a 2 instead of a 3, right? Right? Okay, so now we're done. Remember that in these factoring patterns that we just looked at, remember that the quadratic part of the sum and difference of cubes patterns is always going to be an irreducible quadratic. It's never going to ever factor. It will always give you imaginary roots every time. Okay? So then all we'd have to do on this problem is once we get to here, I can stop because now the largest of my factors is quadratic, and so I can just set them all equal to 0 and solve, right? And some of them I'm just done, right? This one we already know. I get x equals 0. That one's -3. That one's -2. What about in here? Well, in here I'm just going to set that equal to 0 and solve, right? So what happens if I do that? If I set x squared minus 3x plus 9 equal to 0, I'm just going to use the quadratic formula, right? Yeah. Right? So a is 1, b is -3, c is 9. So I'm just going to get x equals -b. So that's going to give me +3 plus or minus the square root of b squared minus 4 times 1 times 9. All over 2, right? So now watch what happens with this, because this is also another really important pattern. You guys, right now, you guys should really be tuned into this, because there's a ton of stuff going on here. If you're not, you just get there. So this is going to give me x equals, if I split that up into two parts, I'm getting 3/2 plus or minus. Well, what's this? I get 9 minus 36 is -27. The square root of -27 is going to be what? How can I simplify that?
Is it going to be 27?
Okay, square root of 20, right, but the square root of 27 itself, I'm going to get a negative number there, so I'm going to get an I out of it for sure. But what about the square, what about the real part of it? Okay, good, I'm going to break that into the square root of 9 times the square root of 3, so 3 radical 3, right? So then the other part of this is going to be 3 radical 3 over 2 times I, right? Okay, notice what we got there. We got two complex solutions with imaginary parts, and they always show up as complex conjugates. A plus or minus BI. They're always going to come in those packages of 2. Remember talking about that a little bit, that week before break, right? We said that when you follow that fundamental theorem of algebra, we know that for a 7th degree polynomial, we're guaranteed we're going to get 7 complex roots, right? How many possible real ones could we have? Well, we could have all 7. Could we have 6 real roots if it's a 7th degree polynomial? Because if I had 6 real, that would leave 1 imaginary, right? What's wrong with that picture? They come in pairs. They come in complex conjugate pairs. So they always. So I couldn't have 6. I could have 5 real and 2 imaginary, or 3 real and 4 imaginary, or 1 real and 6 imaginary, or they could all be real, right? But I can't have. I can only have even numbers. They have to come in packets of 2. All the imaginary ones, right? So here's my 3 real solutions. Well, there's 2 imaginary ones that came in a pair. They came in a packet, complex conjugate pair. What about this guy right here? If I set this equal to 0, I'm just going to get x equals -b. So there's my +2 plus or minus the square root of b squared minus 4 times 1 times 4, right? All over 2. So that's going to give me x equals 2 over 2 is 1 plus or minus, what's the square root of -12? -2 radical 3 over 2. Well, those cancel, right? So I end up with x equals 1 plus or minus square root of 3i. Another pair of complex conjugate zeros. So there's my 7, right? I get 1, 2, 3 real, and 2, 4. 2 pairs of 2. So 4 imaginary. Okay? Make sense? Okay? Let's look at just one more. I'm just going to pull one up. I just made some new ones.
Got 6 cents.
We can do it.
Are you recording?
Yep. Okay, what about this one? What do I do?
2x over.
Move the 2x over, sure. Okay, move the 2x over. Could I do anything else? Could I simplify this right away? Divide by 2. Can't divide by x. If I divide by x, see what would happen if I divided both sides by x. I would end up with x to the 6th on this side and x to the 6th and nothing on this side. So how many total solutions does that give me?
1.
By the fundamental theorem of algebra, if it's a 6th degree, I get 6, right? But that's not right. How many should we actually have? 7. So if we divide by x, we're losing 1, right? Yeah, we can't do that. We want to get all of them. So we could divide each side by 2. That helps. If I divide each side by 2, I get 64x to the 7th equals x. Now I could subtract the x to the other side, right? And get 64x to the 7th minus x equals 0. Now what?
Would be
Pull an x out. And this takes us back. Once again, this takes us back to Unit 2. What did we say in Unit 2 we always want to try to do? Always want to try to factor out these GCF, right? Every time. So I can take an x out, leaving me with 64x to the 6th minus 1.
You've seen this now.
Okay, now,
You just do x cubed squared.
okay. Okay, so now how do I look at this? I could look at this as a difference of cubes if I think of this first term as being something cubed, right? Well, what is that cubed? 8. 8x squared cubed, right? Does that make sense? Okay. Or what else could I do?
You could also do.
Couldn't you cube both of them and you get 4x squared minus 1 over 1 negative 1 cubed?
That'd give you 9.
Well, I can't cube anything, but there's two different patterns I could use here, right? I could think of this, let's write them both down. So we could rewrite this as, we just said we could rewrite this as 8x squared cubed. Hold it, no. It'd be 4x squared cubed, right? Okay. We may not finish this one. Minus 1 cubed,
Got about 3.5.
right? Okay, or we could write this, we could think of this as a difference of squares. We could think of this as being 8x cubed squared minus 1 squared, right? Okay, this is an important point. This is why I've never even think about touching this with a regular class, but for you guys, this is something I want you to think about. Only one of these is going to make sense. Okay, and we're going to run out of time. But if I try to do this one, let's just plow ahead with what's going to happen. If I try to do this one, I'm going to be following a pattern here where I'm going to end up with a difference of cubes, right?
Yeah.
So if I were to factor this one down,
It'd get pretty complicated.
it's going to get complicated, but it's going to get complicated in a way that's going to be not very fun. I'm going to end up getting something like 4x squared minus 1, right? A minus B times A squared.
Yes.
So that's gonna give me 16x to the fourth, plus 4x squared plus 1, right?
Yeah, it's always plus.
Okay, that one's not hard to solve, but what are you gonna do with that one? Yeah.
Does the right one work? It's negative 1 squared. Negative 1 squared is 1. Not negative 1.
Yeah,
Minus, no, it's minus 1 squared. 1 squared is 1.
minus 1.
It's not negative 1 squared, it's just positive 1 squared. It's a difference of
What's
squares.
the difference?
Yeah, difference of squares. Do you guys see that that's gonna be a problem?
Yeah, because you just got to do it again.
How are you gonna do that? This one doesn't show up as being, now, what could I can't really make that packets of anything. I guess I could make it packets of
4x squared.
2x, right? Packets of 2x that are being squared. Or 2x squared that are being squared. But what are you gonna do? I mean, I know I'm gonna run out of time. But if I write that as 2x squared plus 2 times 2x squared plus 1. Is that right? Yeah.
Yeah, that's right.
How- That's not gonna work very well because I've got something squared plus 2 times something plus 1. Magic numbers exist, but look at those magic numbers. You're gonna get 2x squared plus 1 times 2x squared plus 1. And that's gonna be a mess, right? How much time we got? Okay, I'm just gonna bail. We're gonna need more time. We're not gonna get it. We'll come back to that. We'll come back. So real quick, one last thing. So what I'm gonna do for you guys, I'm gonna put up the assignments. I'm gonna put very small assignments up, just in small increments, like, like 4 problems per assignment. We're gonna do a few of these, right? But I'm just gonna do it piece by piece. All right. Yes.